today I'm really happy to be talking about a possible future for performance-oriented software that sits right between pure functional programming and systems aid at restricting aliasing. So without further ado, let's get started. And to set the stage, let me tell you a little story. So picture yourself as a developer in a respectable software company that sells a fancy video editing app. And because performance is a real concern in this domain, the app has been developed in C++. All right, so now don't be alarmed. Thanks to a lot of refactoring, the code base looks actually quite nice. So it's okay, it's good C++. And today you've decided to take on this issue, implement list exclusion. The description looks reasonable. There is even an example, but you're a little bit rusty when it comes to algorithms. So you ask a friend for some help getting started. And your friend sent you this very elegant piece of code written in Haskell. She's usually a very good programmer. The algorithm is relatively simple. There is nothing to do if the second list is empty. Otherwise, we look for an index of an element in the first list that's equal to the head of the second list. If we find one, we recurse one time to remove all occurrences of the head, and the second time to remove the other elements of the second list. If we don't find any, we recurse to remove the elements in the tail of the second list. This is a very simple and beautiful algorithm. It looks so simple, in fact, that you decide to transliterate it directly to C++. And this is what you get. So, of course, it doesn't look as nice, right? Let's not go into the details here. But to be fair, C++ isn't a functional language, so it makes sense. We don't have pattern matching, and it's not an expression-based language. But anyway, it's the same algorithm as before, so it should be fine. You can submit your pull request and head back home. Unfortunately, the next day, you discover that one of your colleagues didn't really like the transliteration. They seem to want a more imperative-oriented approach to the problem. And so they wrote this comment. And beyond aesthetics, they might have a point about the number of small allocations you made in your function. C++ is not a managed language, so allocating and deallocating memory on the heap is typically an expensive operation. So keeping everything immutable, like in the Haskell version, might not be the best option because it's causing a lot of wasteful copies to store the intermediate result. Okay, so you start refactoring. And here's what you end up with. It's almost the same algorithm as before, only now it uses loops rather than recursion, and it mutates the result in place as it goes. So let's go over this version. For each of the elements in the second array, we look for an index of equal elements in the first array. If we find one, we erase the element at that index and look for another index in the remainder of the first array in case the element occurred more than once. It's basically the same algorithm as before, but using loops. And now that you look at it, your code is actually quite elegant for a C++ piece of program, right? Maybe mutation is not so devilish after all, and you can submit your pull requests feeling really proud of yourself. And you can go back home and be sure that your colleague will really appreciate this new version. Unfortunately, the next day, ouch. Again, change requested. And this time around, you find the complaint a little puzzling. What do they mean by too slow? Sure, the complexity of your method is a bit high, right? It's n squared, but the issue that you resolved didn't mention anything that you could use to bring that down. We're talking about lists, not sets, so really you can't do anything better, right? And what do they mean by mutate X in place? You did mutate in place, so what is this reviewer complaining about? Anyway, you pocket your pride and go see the reviewer to get a sense of this comment. And it turns out that the problem with your implementation is that it's still creating wasteful copies every time it gets called. And that's because in C++, there is something called value semantics. Because subtract here takes its parameter by value, so like this one, C++ makes a copy so that X becomes an independent value in the scope of the method. The same goes for Y. And Copying is fine for small data types like integers or booleans, but it becomes an issue with larger data structures. Here, for example, it's quite expensive to allocate a whole new storage to copy S, which presumably is quite large, right? It's the result of a very large array operation. And we will destroy the storage right after the subtraction to reassign it to S. So by the way, you may notice that this statement here is a functional update, right? It's the classical way one implements mutation in functional programming languages. So the problem with your code isn't that you implemented an inefficient algorithm, but rather that you implemented that algorithm inefficiently. And this is a concern we have when we are dealing with systems programming. But the reviewer not only pointed to a problem, he also offered a solution. The only thing you had to do was to use references. And so you follow his advice and you take X as a mutable reference so that you can mutate it in place without causing a copy when you call the function. And you take Y as an immutable reference because, well, you won't modify it. Also, you no longer need to return any value because now you just mutate the first parameter, so you can get rid of this return statement. You commit your change, and this time around, wonderful, success, your pull request did merge, and the company made a lot of money thanks to your list exclusion algorithm. But of course, the story doesn't end here. A couple of months later, you spot this issue popping on the tracker. Oh no, you hadn't tested subtracting a vector by itself. And now that you think about it, you have a pretty good idea of the problem. If X and Y are the same array, then iterating over the latter while you're removing elements from the former will surely mess with your indices and will cause a bunch of issues, like in the example here. So you go back to your code to fix the problem. Well, rather than iterating lively over the second vector, you'll start from the last element and make your way back. So if X and Y are different vectors, this line will decrement I every time. If they are the same, they will assign I to the last element of the second array. Well, this works. Sadly, it looks not as good as before, right? This code is getting complex, but at least it's not buggy anymore, so you can close the issue. The problem is that, to your surprise, you find another issue still complaining about your subtract method. I'm guessing that you're starting to regret taking on this task, right? But anyway, once again, you have a pretty good idea of what's causing the issue. Indeed, if all items happens to be the same reference as unavailable, then calling your method will clear the latter. It's the same problem as before, really. It's just shared mutation, but this time it's not really your function to blame. You handled the case where X and Y were referring to the same objects. So instead, the blame is on any code that doesn't account for this scenario, like presumably the code of the issue reporter here. So the best you can do on your end is to add a warning to your method's documentation and hope people will be more careful when they use it. But this is hardly a good solution, isn't it? Despite your comment, using your method is now error-prone. And admittedly, the fact that Y may change, even if it's declared const, is a bit confusing. Also, a couple of months later, you start to notice this pattern is recurring quite often in the entire code base. And this is called a defensive copy. It's defensive in the sense that copying unavailable, which is what this line is doing here, will prevent unintended mutations when the referred object is the same as all items. In all other cases, however, this is a completely useless copy. And in fact, it's recreating the performance issue your function had when it didn't use references. So it seems like we made no progress at all. And the only way to get rid of these defensive copies is to add warnings or preconditions all over the place, like in all the functions, and trust that no one will make a mistake. And well, this is, I think, completely unrealistic in any large code base. So yeah, this picture is pretty bad, and maybe you're not surprised, right? C++ is a hot mess after all, but don't think this problem only concerns C++. In fact, my favorite example comes from Java. In an early version of the Java platform, there was a security issue that could be exploited to to access data that you were not supposed to access, right? To escalate privilege. See, in Java, a class has a field containing the identities of its so-called signers. It's used by the system to restrict or grant access to certain features. And so the exploit consisted of taking a reference to these identities and modify them behind the back of the class. And what's interesting here is that none of the standard Java mechanisms can protect you against this exploit. You're not reassigning signers, you're just providing reference. And it's because of the shared mutation that we get into trouble. So what was the fix? Well, it was actually a defensive copy. And this copy here serves to protect the field against the annotated mutation, because now we produce a new array that we give to the user. So if that array changes, we won't get impacted by the mutations. But it would be certainly be nicer if the language had a way to expose this value while guaranteeing it won't change, rather than expecting users to insert potentially expensive copies defensively almost everywhere. And you can certainly become paranoid when you have to work with this kind of threats in your code base. So what's the moral of our little story? Well, mutation is the root of all evil, right? This is certainly the answer you'll get from the Haskell enthusiast we had in history. But in my opinion, the culprit is shared mutable state. In fact, if we look at this version, it's the first version that we had using loops. Was actually quite nice, and it did feature mutation. Things only started to go wrong once we added references. This version offered a really nice property, local reasoning. And in fact, it's completely safe and fine to mutate a value as long as we can reason locally about the effects of this mutation. Here, because the arguments are passed by value, neither us nor our clients need to worry about a mutation of X having a side effect on Y. So note that pure functional programming also gives us local reasoning, which, by the way, I think is actually more important than referential transparency. But it also robs us from the ability to express mutating algorithms naturally. And sure, your optimizer can do wonders to recover efficiency, but it's not always easy or even possible. So if we can argue for days about the functional versus imperative programming in terms of subjective qualities like, I don't know, elegance or ease of use, what's less debatable is which of these approaches most closely describes how actual hardware operates. And if you care about performance, like because you're writing a video editing app, you might not have a choice. So would it be nice if we could enjoy local reasoning in the imperative world without the constraints of immutability and without having to pay for expensive copies to implement pass-by-value semantics? Well, if you know a little about Rust, you know the answer. And the answer is yes. So let's have a look at this Rust thing. Okay, so on the right, we have our subtract method, the one with the expensive copies for the pass-by-value. And on the left, we have a transliteration of this code in Rust. The body of the function is almost the same as in C++, so let's not delve into these details. Instead, let's focus on the signature. The first thing to note is that Rust has a linear type system. So when we pass arguments by value, like here, they get moved into the function. And we'll see what's the implication for the caller in a minute. The mute keyword tells us that X is a mutable in the scope of the function, which isn't the case for the second argument. However, note that Y is also moved into the function. It's also passed by value. Thanks to these semantics, X and Y are known to be unique in the scope of the function. They are passed by value, just like in C++. So there cannot be any outstanding references to either of these values, and mutating X cannot possibly have a side effect on Y. We have local reasoning, everything is great. And at the call site, we can see that moving an object doesn't create a copy of its notional value. So that means we can call a function like this without the wasteful allocation we had in C++. The storage of S is transferred to subtract, which can mutate it as it sees fit before being transferred back to reassign S. So this is what is meant when we're talking about linear objects. They are unique, and using them doesn't create copies, at least in general. So that lets us write functional updates quite efficiently. Of course, if we transfer the storage back to another variable, we won't be able to use s. So here, for instance, I'm assigning the result of subtract to t. So if I try to use s again, we'll get an error. And the error makes sense, but what is the message about, really? Well, actually, Rust might be better known for its borrow mechanism than for the linearity of its objects. A borrow in Rust is equivalent to a reference in C++, but it comes with much stronger guarantees. To understand, let's have a look at the version of subtract that got us into trouble, right? The version that had all the references. So in Rust, it looks like that. The &mut denotes a mutable borrow, while the & alone denotes an immutable borrow. These are equivalent to mutable and immutable references in C++, respectively. An important difference, however, is that in Rust, a mutable borrow is guaranteed to be the only live reference to the referred objects in its scope, and the value of an immutable borrow is guaranteed to remain unchanged while the borrow is in scope. In our function, that means, once again, that a mutation of x cannot possibly have a side effect on the value of y. So we still have local reasoning, even in the presence of references, which was clearly not the case in C++. So at the call site, Rust will catch violations of uniqueness at compile time, and it will prevent us from repeating the mistake we got in C++. Right? This was the call here that created the invalid results, and this is caught as an error in Rust, which actually is quite nice. So it would seem that Rust has everything figured out, problem solved, and we can all head back home. But before we do that, let's look at one more example. This C++ function accepts two immutable references to character strings and returns a reference to the longest. There's really nothing fancy here, right? It's just if x is longer, then return x, otherwise return y. So let's try to transliterate this function to Rust. We said that immutable references are equivalent to immutable borrows, and this is the syntax of immutable borrows. So this should do the trick, right? Well, sadly, it doesn't. And the problem is that this function is returning either of the borrows, and so Rust wants to have this lifetime specifier. But what is a lifetime specifier exactly? Well, this is how that looks. An identifier prefixed by a tick denotes a named lifetime in Rust. This is kind of a generic parameter that we can put on functions, and it is used by the type checker, or more precisely the borrow checker, to reason about the lifetimes of all the parameters and return types involved. So when the borrow checker looks at a call to this function, it will use the annotations to infer the scope in which the return borrow is safe to use. But what is the purpose of this thing? Well, the mechanism serves to catch the following problems at compile time. In this example, we're creating two local variables, one character string and one vector containing a second character string. We then use a longer of to get the longest of these strings, and we clear the vector before we finally print the string. Of course, because we cleared the vector, the memory of the longest character strings is gone by the time we reach this statement. And this is caught as an error in Rust. We will not be allowed to clear the vector because there is a borrow extent by the memory of this vector. In C++, however, the same statement has undefined behavior. So the compiler will be happy to compile this program, but the program has undefined behavior, meaning that it can crash, produce incorrect results, or even open a security breach. So this is quite a serious issue. So lifetime annotations are a very nice mechanism. It's super powerful, but it's also kind of complex to use and can go out of hand, like in this example. Here we defined 3 different lifetimes to describe the possible references of our decode results type. So we have buff, which is the lifetime of the buffer that we have, and the columns indicate that this lifetime must be longer than decoded, right? We can have relationship between lifetimes. This second lifetime is the lifetime of the decoded objects, and we have yet another lifetime that is the lifetime of the labels that we might want to associate with our object. So all of that is getting quite complex. And Well, I think that's an issue. To be fair, though, this kind of situation doesn't occur so often in real Rust, but nonetheless, I've yet to meet a Rust developer who doesn't nod along when I say Rust lifetimes can be a real struggle. And the phrase fighting the borrow checker has become a kind of recurring meme in the Rust community. And there is also the mere complexity brought by reference types in the first place. For example, while preparing the slides for this talk, I stumbled upon this head scratcher. I copied this line from the Rust documentation, the iter position blah. And position is the method that gives you the index of an element in a collection. But then I got hit with this error message. It's a bit puzzling because it's not completely obvious here what sharing occurs. Where is anything shared? So as far as I understand, the problem is due to iter here creating a borrow. And this borrow is causing A to move later on. But to be perfectly honest, I would need a Rust expert to confirm. So anyway, I removed the ampersand, and then I got hit with another error message, this time complaining that %t is not comparable to t. This error is a little easier to figure out, right? The problem is that a reference is not comparable to the referred object. So the fix is to dereference A, and there we go. So eventually I got my code to compile, but this little example captures a common fight with the borrow checker. To be fair, the compiler produced quite helpful error messages. So if you know your basics, you should be able to converge toward a solution relatively quickly. But still, I don't consider myself a complete beginner, and I found this exercise relatively difficult. It took me a while to get it right. And well, I would say writing closures in general isn't that hard in other languages. And I think part of the issue is due to the fact that a reference to an object has a distinct type in Rust, which just adds complexity to the system overall. In most modern programming languages, the user doesn't have to care about this distinction. So if we want to write this line in Kotlin, no references, no dereferences, no ampersand or star involved, same in JavaScript, I think it should look like that. So to sum up this little chapter on Rust, we can see that aliasing restrictions gives us the safety net we need to maintain local reasoning in a world of references, but it comes with serious complexity costs. So can we do anything better? So here is an idea. What if we just remove references from the equation altogether? In fact, this is the idea behind mutable value semantics. Not only value semantics like we saw in C++, but mutable value semantics, or MVS for short. So you take your language and you remove any form of reference. No pointers, no global variables, no closures, no reference at all. Of course, this sounds like a very drastic measure, but how much expressiveness do we actually lose? Well, the goal of the remainder of my talk is to convince you that we actually don't lose that much. And to delve deeper into this idea, let me introduce the project I'm currently working on. Val is a programming language I'm developing with a handful of amazing people, mostly from the industry. It is set to have a transparent performance model that lets users rely on guaranteed optimizations to predict memory allocation costs, and it's set to be safe by default. Here, safety should be understood as freedom from undefined behavior. And if you don't come from the C++ world, undefined behavior denotes a situation in which your program could do literally anything, including starting to interpret arbitrary data as code, hence the open security breach issue. This kind of safety isn't actually very hard to achieve. Haskell is safe, Java is safe, and most scripting languages like JavaScript or Python, well, they are also safe. But the difficulty is to avoid taxes at runtime while keeping the language expressive enough. And this is a concern in a domain like C or C++, where people really don't want to hear about garbage collection or anything expensive at the runtime. So these two goals translate into the following research question. Can a language enforce the guarantees of because our research started with Swift which is a programming language developed by Apple that has a pretty good support for mutable value semantics. But Swift relies on copy and write to mitigate the cost of copying. And though Swift is quite fast, copy and write does incur a runtime cost that for some people is just unacceptable. And this runtime cost is really difficult to avoid when you write Swift code. So anyway, how does our subtract method from earlier looks like in val? So here again, on the right, we have the Rust version, and on the left, we have the val version. It's quite similar to, the val version is quite similar to Rust and C++. So let's focus on the significant difference only. The sync keyword here specifies a passing convention, a parameter passing conventions. All types in val are linear, just like in Rust. However, unlike in Rust, val never copies anything implicitly, including simple types like numbers and booleans. So absolutely all copies are explicit in val. The sync convention signals to the caller that this function, the subtract function, will take possession of the first argument. In other words, the argument will move into the callee without causing a copy. It's really the same thing as what we had in Rust before. The let keyword signals to the caller that this function will only read the second argument without modifying it. And this is the first significant difference with Rust. A let parameter is the numerical equivalent of an immutable borrow, but in val it doesn't have a different type. Inside of subtract, y has the type array of t, and no reference is involved. So from the perspective of a val developer, it's simply a parameter passed by value, and there is no need to think about anything more complex than that. The copy can be avoided by following the observation that if the argument is guaranteed to remain alive and unchanged anyway, by the rule of the immutable borrows, or in the case of val of let parameters, we can safely take a reference under the covers at the implementation level. So it's fine to use references, but only at the implementation level. In the user model, we don't need to have references. Another difference between val and Rust is that the ampersand in val doesn't relate to references. It's only a mutation marker that we need to place on any variable that may be mutated, when it's part of an expression. So here, for example, we need to mark X for mutation because we are calling remove on it. It's a mutating method. And on the next line, we need to mark J for mutation because we are assigning it to it. At the call site, we get the same behavior and the same guarantees as we had in Rust. So here, S is sunk. That's the name of the seek parameters. S is sunk into the callee and reassigned to the return value without causing any expensive copy. So that's, again, an efficient way to implement functional updates, just like we had in Rust. And of course, as in Rust again, we can't access S after it's been sunk. Its value has moved, right? So values have this linear property. So the fix here consists of making an explicit copy. I said before that we have explicit copying in val for all values involved. So making the copy here creates an independent value that we can just sync into S, and we still have into subtract, sorry, and we still have access to S for the second argument. Now the in-out convention is another one. We saw sync, let, the third one is in-out. It denotes in-place mutation. So here the first parameter is taken in-out, and this version of subtract is the one with the references that we had in C++, right? The one that caused all the troubles in C++. So the moral equivalent of an in-out parameter is a mutable borrow in Rust, and it has the same guarantees. But again, it doesn't have a distinct type. For the perspective of the programmer writing the subtract method, X is just an array of int. It's not a reference or pointers or anything like that. And another difference is that the callee is free to do whatever it wants with the in-out parameter, as long as it puts a value back into the parameter before the end of the callee. So whatever it wants means also consuming it, like syncing it into another function. So that means that if we have both versions, like we have the subtract version that operates by reference, and the subtract version that operates with this pass by value semantics, Well, in val, we can implement one in terms of the other because there is an equivalence between these two forms. So in this example, we have the in-place version that's using the in-out parameter, and this in-place version is allowed to use the sync version. So we can move out the x and reassign x, and nothing can be seen from outside of this code. The same code doesn't compile in Rust, and that's because we cannot move a value out of a borrowed reference in Rust. So I believe this limitation could be lifted, but once again, it reveals the drawback of having references as distinct types. In val, x can just be felt as a value of type RFT, and it's guaranteed to be unique, and so you can do whatever you could do with any other value that has the same properties. So nothing else needs to be considered. So the correspondence between functional and in-place updates is very real, and in val it can be captured in a feature we call method bundles. So in this example, subtract has been redefined as a member function in an extension of array, and it's defining two variants. The in-out variant corresponds to the implementation of the version taking the first parameter in-out, which I won't repeat here for conciseness, but it's exactly the implementation we saw one slide before. And the sync variant corresponds to the second version. But as we can see, we can implement it in terms of the former thanks to this nice property that we have that I explained already. This bundle, using this bundle, the compiler can select on its own the appropriate variant depending on the call site. Here, for example, the compiler will select the in-out variant because we want to mutate S in place. This can be determined from the fact that we have a mutation marker on S, and S is used once more after the call. So presumably we still need the value of S. On the other hand, in this second case, the compiler will select the sync variant because the call is the last use of S. We don't use S after the call, so we can as well just let it move and be sunk into the method. So this approach here allows us to make links between the different versions of the same function we have between these different semantics, and have the compiler figure out what is the best version to use. And in this example, we just implemented sync in terms of in-out, but we could have situations in which it might be better to have a custom implementation of sync because we can leverage some properties to better reuse storage or something like that. The last feature I'd like to present before I close is subscripts. Subscript can be used in situations where one would return a reference in Rust or C++, like in the example we discussed before, right? The longer of function that returns the longest of two character strings. So in val, unlike a function, a subscript doesn't return a value. It projects one into the scope of its useful lifetime. Okay, that's a mouthful. So what do I mean by that? The same program as we had before, right? So we create a character string, we create an array with a string inside, then we call longer off, and then we try to clear the array. And this is an error that val is equally capable of detecting than Rust. And here the problem is that we have overlapping mutations. So when I say the projection is for the duration of the useful lifetime, one way to think about it is the useful lifetime of S starts from the moment it's created to its last use, which is the print statement here in this program. So another way to understand how this works is to think of a projection or subscript as a function that accepts a lambda or a higher order function, right? And this lambda is getting called with a let or in-out parameter representing the projected value. So this is an equivalent form of the program we have. Longer of is now a function that accepts a third parameter representing the lambda in which we want S to exist. And so by the rules we had before, if a let parameter isn't allowed to mutate and must be live for the duration of the call, then it's not really hard to see why this mutation here is illegal, right? because it's deleting the memory of the let parameter. And of course, that cannot be allowed because it would violate the rules we set for let parameters. So projections are a way to do that with references that would otherwise be returned from a language like Rust or C++. And notice that we don't need the lifetime annotations that Rust had. Our subscript longer off doesn't have any annotations. And that's because of this trick with the lambda here. Now we can easily control the scope of the lifetime without requiring annotations to keep track of that. All right, so before I close, there is one last question I'd like to answer with this talk. And this question is, what about the doubly linked lists? So as you may have suspected, Rust's insistence on uniqueness means that there is no way to represent a mutable doubly linked list using borrowed references. Right? If you have a borrow, it needs to be unique, and if it's mutable. And so if you can only have one mutable borrow on a node, then it's definitely impossible to implement the doubly linked list. And the same limitation applies to val, because val doesn't even have references. So there you go. And projections are meant to be stored. Right? Projections are like bindings, and are meant to be used in a scope, like we've seen in a very simple example. So you can't represent doubly linked list in val either. That's here one of the expression of limitations that I mentioned in the research question before. And that's actually a big deal. I agree. So losing the ability to directly access data through references or pointers definitely changes the way programs can be written. There are some ways to work around the problem of the double linked list. You could have adjacent lists, for instance. But yeah, it's a change. You cannot just take your average Java program and translate it to Rust or translate it to val. But in exchange for this loss of references, you get local reasoning, and you get guaranteed performances, because now we no longer need the wonders of an optimizing compiler to recover in-place mutation. So I would argue that these limitations are actually a win, because they make programs simpler to understand, thanks to local reasoning, for both humans and machines, and easier to optimize, again, thanks to local reasoning. So this is really a win. And I think it also offers true potential to revisit techniques that have worked for pure functional languages in the context of imperative ones. Because now we are free from the challenges of aliasing. So we can explore type states or liquid types, refinement types, and all of these techniques that are really, really difficult to achieve in an imperative setting due to aliasing. And if you need to remember only one thing, that's the takeaway I'd like people to think about. Like, the restrictions that we impose with value semantics are actually a win for the understandability and the optimizability of your code. Anyway, that's it for me. Thanks a lot for your attention.